Hi, good evening, everyone. And today, as I mentioned here in my slide, that I'm going to take care of again gate level modeling. If you all remember that in last class, I have covered that a basic implementation of your gate level design on slide that I'm going to take care of again. Okay, so gate level implementation, or I can say the schematic implementation of FPGA. Okay, so the concept is that I am I'm going through with very basics, and as I mentioned in starting that I am covering both digital, Verilog, and FPGA in parallel. Okay, why? Because unless until we don't know the digital concept, right, we cannot use the syntax available in Verilog. So if we don't know the how the mux is working, how the 2s complement is working, how the sequential circuit is working, okay, how we are going to use the syntax available in Verilog, right? So to use the syntax available in Verilog, we need to understand the working functionality of the digital. So that is why I have started with the digital, okay, but I have covered till schematic design of 4-bit, 8-bit adder using both a single line and multiple bits, right? So now I'm focusing on Verilog because uh, with the help of Verilog, we are going to design the each and every component. So in my first two class, I have guided you that how to design the full adder and half adder, or I can say the half adder with gate level, and then full adder with help of two two half adder with the gate level modeling. So basic introduction I have given, right? So now today onwards, we are going to start some more concept used in Verilog. So for that, you have to keep patience for next 1 hour and follow the class schedule mentioned in the headline, that is the class 18, class 19, class 20. So in this way, you can easily connect the classes. Okay, you will not forget that, okay, or you don't have to worry about that which class I have to follow now. So I'm going through in such a way that you should follow the schedule and you should follow the connectivity without any problem. Okay, so okay, this one. So very important gate level, very important topic we are going to cover today in gate level modeling is about X and Z. X and Z, right? So this X and Z is also a part of the digital electronics. This X and Z is also a part of the digital electronics. So basically, I have not shown you that how it is a part of the schematic. Today, I am going to cover both about X and Z, both used in Verilog and also used in a schematic. So please be focused. If you don't know anything or if you have any query, you can send me a WhatsApp message and then I will reply. Okay. Okay. So as I mentioned, gate level modeling. Before starting, let's focus what is X and Z in digital and Verilog. Okay. As I mentioned here in slide, that X is basically a known or don't care state. We are also aware about the X in K-map. So here unknown means which is not defined. Okay. I will show you practically also. So meaning that the value of unknown is or undefined is the meaning, that is the value of unknown, the value is unknown or undefined, that is we have not given any source 0 or 1, we have not provided any source, that is why this is called as X. It could be either 0 or 1, that is I mentioned, but we don't know which use mainly in, Okay, which is exactly it is 0 or 1, right? So as per the statement, what is x? X is the unknown or don't care state, meaning is the value is unknown, we are not aware of it, and it could be either a 0, but we don't know which, right? Now mainly you can see the x in simulation. Okay, I will show you in simulation. When signal hasn't been initialized, logic design simplification as don't care condition in K-maps. Okay, so if you know the K-map, maybe you aware of the x, and maybe your faculty member has taught you that what is x. X means unknown. If circuit output is marked X, it means that designer or simulation determine whether it is 0 or 1 or at that moment. Okay, the same thing. Okay, but here one basic difference which it is not added here, that let me add it here. Okay, so the this X is always in simulation. You can see at the output side. Okay, I will let you know. Right, I will show you how. Right, because why it is output side, because it is connected with the basically the input. Okay, so the another slide is basically a is at the input side. Okay, again at the input side. Okay, so let me show you. So please remember this as I mentioned here, please remember this z is always represent at output side. Okay, please remember this line. Next. Now, input high impedance state Z, meaning that the output is electrically disconnected, like an open circuit. Okay, it can be electrically disconnected, right? Means uh, that it is a floating state. Okay, we are not aware that it is either a 0 or 1. Okay, it is neither a 0 or 1. It is basically a the line is effectively a floating state. Tri-state buffer, shared buses. Okay, where device is not using a bus, it sets output to Z, so other device can safely use it. Okay, this line is again not exactly related to our stuff. Okay, but if I say that in Verilog, this this Z is basically at input side and X is always at output side. Okay, so but please remember this line. Okay, please remember this line. This line. Okay, the output is electrically disconnected. Okay, so now I'm going to add my content here, that we have an input and we have an output. Okay, so at input side we can force both X and Z. Okay, we can force both X and Z. Okay, please try to understand what is X. X is basically unknown or don't care. The value is that it could be either 0 or 1. That means it can be either 0 or 1, but we are not aware about the source. So from where we will start the source? Source will start from the input side. Okay, so that is why this is my, if I'm taking a Z as a source, for example. Okay, but if Z is my disconnected, meaning of Z is means disconnected, nothing is available, right? Nothing is available at the source side, then we are not aware about the output, that what will be my output. Okay, what will be my output? So in that case the output is X. So this is the relation between the Z and X. Okay, again let me again explain. Let me again explain. Okay, so X means unknown. Okay, and Z means floating state. Okay, floating state. Let's take these two simple lines. Okay, so when the x will come and when the z will come. So whenever we are forcing, whenever we have any gate, okay, let's take example of gate, and this is the input side and this is the output side. Okay, so suppose that if I forget to connect, suppose that I forget to connect any source at input side, that is a 0 or 1. Okay, so what is 0? 0 means low strength, 1 means high strength. If I forget to connect any source at input side, I'm not aware about what is my output. Okay, so disconnect or floating state input, that means this is Z. Okay, so generally in Verilog, if you will come across all these things, you will find that this Z is always at input side and this X is always at output side. Okay, this Z is always at input side because it is a floating state, right? It is disconnected. We are not sure that what we are going to connect it or what we are source we are going to provide it. Okay, so this is one thing. So I will change some lines in these slides. Okay, so again, a basic comparison here, that the symbol X means unknown, could be 0 or 1, uncertain again, and simulation don't care cases. Okay, this is a basically a use case. So see, just for example, this X can be come as input. We can give as output also. Okay, so this X you can see at input side also, at output side also, and this Z you can see only at input side. Okay, only at input side. In maybe some cases, then we will see at that time. Okay, unknown high impedance could be 0 or 1, disconnected, floating, and what, and basically I can see the X and Z in the simulation, in don't care cases, in tri-state logic, and in buses. Okay, so we are going to use this also, right? I hope this is clear to everyone. Okay, so this X and Z is basically you can say that it's the like values, okay, in digital. So like 0 and 1 is a part of digital. Similarly, X and Z is also a part of digital. X means unknown and Z means floating. Okay, floating state. So here the priority is given as per the gates. Okay, for example, okay, for example, okay, for example, this is AND gate. Okay, let's take a AND gate. Okay, so in AND gate, the input is 0 or 1. So priority is always given to 0, right? Priority is always given to 0. Okay, as we know. Okay, so whenever any input is 0, whenever any input is 0, you know that output is 0, right? Okay, I'm still discussing about the X and Z. Okay, so whenever any input is 0, output is 0. But if any input is coming along with X and Z, okay, if any input either 0 or 1 is is showing along with X and Z, then what is the output? Okay, so let's discuss that also. This is a one series. Now let's take 0 and X. As I mentioned that I can give input X and Z also. Okay, So in that 0 and x, the priority has been given to 0, output is 0. I will show you practically also. Okay, 0 and x and 0. So this is the one series. Okay, now let's take 0 and z. 0 and z, output is 0 because priority has been given to 0, and z and 0. Okay, this is a one series. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, now still we have some more options left. Okay, I'm talking about this same AND gate. Okay, A, B, and out. Now X has been done and Z has been done along with 0, right? But when input is not 0, but when one input is not 0, it is one X or Z, then in that case, what will happen? So let's take 1 along with X and X along with 1. So in that case, the priority has been given to X. Okay, what is unknown? Floating state. I don't know it is 0. Sorry, it is unknown state. I don't know it is 0 or 1. In that case, the output is X. Okay, similarly, 1 and Z, Z and 1. So the priority has been given to now Z only. Okay, so again the output is X. Okay, and if both input are X, then output is X. If both input is Z, output is X. So now you can see here total 16 combination. Let's see if anything is missing here. 8, 9, 10, 11, 12, 13, 14. Okay, two cases are still missing. So let me see which are those cases. 0x, x0, 0z, z0, 1x, 1z, 1, xx, and zz. So, okay, two cases means, okay, 15. Zx, it can be any input can be x, any input can be z, and 16, xz. In that case also, you have the output is x. Okay, so this is the actually reality. During BTech, if you are learning Verilog, we only aware about the truth table of 0 and 1 in that case of in case of AND gate. Okay, but as we are entering slowly at higher side, now the few more things will come. Okay, the value is x and z. So if you have x in any case or z in any case, then the output is depend on first the priority of the particular gate, or after that the priority will shift to the other value, that is x or z. Okay, so this is the one example of AND gate. Okay, let's take example of OR gate. Okay, so let's take example of OR gate. A, B, OR. Okay, so 0 0 0 1 1 0 1 1. So this is one case. Okay, let me first differentiate. This is one case, this is one case, this is one case, and this is one case. Okay, so 0 0 0 1. So as we know in OR gate, okay, OR gate, okay, 0 and 1. The priority has been given to 1. Okay, the priority has been given to 1. So if any input is 1, output is 1. 0, 1, 1, 1. This is one case. Okay, now 0x and x0. Now this is OR gate output. Okay, so as we know, the priority is now shifted to 1. Okay, so in that case, what will be the my output? Okay, if I'm not getting 1 here, okay, I'm not getting 1 here, right? I'm getting 0. Okay, so don't compare this with this. In that case, if it is OR gate, the priority has been given to x, because it is not a 1 here, it is 0 here. So output is x. Okay, now 1x and x1. Now what is in that case? The priority has been given to 1. So this is 1. Okay. Let's take the other. Okay. Okay. Now, so basically, I have to explain you about every gate. Okay. Otherwise, uh, because this is new thing. If anyone knows Verilog and if he or she don't know about X and Z, then it will be a like a gap. I can say this is a gap. So 0 1 now done. Now 1x. Sorry, I have done with 1x. Oh, oh. Sorry. I will mention here. Right. Sorry. I will take 0z. Sorry. Okay. 0z or z0. In that case, the priority has been given to z because your input is not 1 here. So again, x and x. Okay. Now this is 1x and x1. So now this is OR gate. So the priority is now given to 1. The output is 1. Okay. And then this is one case, then 1z and z1. The priority has been given to 1, output is 1. This is one case, and then xx, output is x, zz, output is x. This is one case, and then zx and xz. Okay, output is x. So I will take at least 2 3 class to explain about this x and z. Okay, this is very important. Okay, now what will happen in case of NAND and NOR? What will happen in case of NAND and NOR? NAND and NOR. Okay, so please try to understand. Means NAND is actually made up of and NOT. Okay, so this is basically your and NOT, and this is NAND. Okay, so what happened in case of NAND? 0 0 0 1 1 0 1 1. So again, it is just the invert of your AND gate. So if any input is 0, output is 1. If both input is 1, output is 0. This is one case. But if any input is 0x, okay, and x0, then what will happen here? Here, if input is 0, that means 0 and x. So 0 and x passed by AND gate is 0, and 0 passed by inverter is 1. So in that case, because this is a NAND gate and this is a made up of AND gate, and AND gate has a priority of given to 0, so this 0 will dominate this x and z, and output will give 0, and this 0 is passed by inverter. This 0 is passed by inverter. Okay, this 0 is passed by inverter, so the output is 1. Okay, so in that case, the output is 1. Very simple. Okay, similarly, 0 and z and 0. Same case, 0 and z. Okay, z. So 0 and z and gate priority is given to 0. 0 passed by inverter is 1. Okay, but now the situation is changed when you don't have the input 0. When you have an input 1 along with x or z, or x or z is the input, in case of NAND, what will happen? Okay, I am talking about NAND gate. Okay, so it is 1z, z1, 1x, x1, xx, zz, zx, and xz. Very important topic. Please, like this. Okay, so now if this 1 Now, if this 1 and Z, then as you know that in 1 and Z, the output is X. As you know that as you know that in AND gate, the output, if input is 1 and Z, then output is X. Okay. So in that case, this is basically your X. Okay. And if this X is passed by inverter, if this X is passed by inverter, then again the output is not X bar, the output is X only. Okay. So let's take a very simple. If this is an inverter, right? If I am giving 1, output is 0. If I am giving 0, output is 1. But suppose that if this input is X unknown, then your output is not X bar unknown, and same output is X only. And in case you are giving input Z, okay, this single input buffer and inverter has few more this has a different truth table if we are going to connect one control signal. Okay, so this I will take up later on, but please try to understand, if any input is X, output is X. If any input is Z, then output is, we will see. Okay, here is a question mark. Okay, so don't need to worry. Okay, okay, so if 1 and Z, output is X and X. Okay, X and X. Okay, so this is a case of NAND. Okay, similarly NOR. Okay, I'm going to share you the truth table of every gate. Otherwise, you will be confused. Okay, okay. Now let's take example of NOR gate. So NOR is made up of OR and NOT. Okay, so priority in OR gate is 1. Okay, if any input along with 1, the output is 1. Okay, A, B, out. 0, 0, 0, 1, 1, 0, 1, 1. The output is 0, 1, 1, 1. Okay, this is a one case. Then 0, x, x, x 0, 0, z, and z 0. This is one case. This is another case. So as you know that this is a NOR gate, so the priority has been given to 1. But if any input is not 1, then priority will shift to x or z. Okay, so in that case, the output is X and X. Okay, so these are the basically your interview questions. Okay, if anyone is claiming that, sir, I know Verilog. If anyone is claiming, sir, I know Verilog, then I will say, okay, let's discuss about the truth table based on X and Z. And situation is clear. If if he or she unable to present the truth table, and I can say that he or she has don't have the good basics. Okay, so this is again an interview question. So you have to be very very you don't have to do a ratification. That is, don't mug up. Okay, just understand the concept, basic concept that what will happen if there is any input is X or Z. Okay, so what is X? X means unknown. Z means high impedance. Unknown means we are not connected anything. Z means high impedance floating state disconnected. Okay, so very simple way you have to understand. Okay, and one more thing you have to understand that I will show you later on. Uh, Later on here in in practical concept. Okay, that is when I will give this input X and Z. Okay, then you will consider the what is the output. Okay, so now let's take in case of NOR A B out, right? So one Z Z1. Okay, so if I give 1 and Z, the priority has been to 1. 1 Z means 1. 1 passed by inverter is 0. So in that case, the output is 0. Okay, 1x and x1. The output is 0. This is one case. This is one case. Okay, now xx and zz and zx and xz. So x, 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 and x. Okay, so we are going to verify each and everything. Please remember this. Okay, so now again, uh, what happened in case of XOR? What happened in case of XOR and XNOR? Okay, so very tricky. I am sure 100% people don't know this. What happened if X or Z is uh, given at the input? What will happen? Okay, so let's see. So XOR is not a gate. XOR is basically a not a gate which is made up of any inverter and gates. Okay, XOR अपने आप में gate है. It is uh, basically one separate gate. Okay, one separate gate. So it is not made up of and or right. And plus there is no connection of inverter. So the implementation of XOR and XNOR is totally different from the previous one. Okay, so what will happen? So this is a symbol of XOR and this is a symbol of XNOR. Okay, so what will happen in case of your input is X or Z? Okay, out. So 0, 0, 0, 1, 1, 0, 1, 1. So you know that whenever the same input, you have a output 0. When you have a different input, plus 1, output is 1. Okay, now what happened if your input is 0 or X or 0, okay, 0 or Z and Z or 0. What happened? So let's see. Okay, so what I will do, I will take another separate page. Okay, and I will design the XOR with the help of NAND gate or a NOR gate. Okay, very simple. This is an interview question. Okay, A and B. So if any input is 0 or 1, right? Just take example of like this. 0 and 1, NAND means 1. This 0 is here, 1. This 1 is here, 1. So 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay, so in this way, basically, you have realized the truth table. Okay, now in case of suppose that you have now one input is X. Okay, now suppose that you have if any input is X and if any input is 1. Okay, or let's take 0. Let's not take 0. Okay, so as you know that if this is NAND gate is made up of and not. Okay, NAND gate is made up of this is your uh, complete NAND and this is simple NAND. So as you know that if I give X and 0 here, so X and 0 passed by AND gate is 0 because priority has been given to 0. Now the 0 passed by inverter is 1. So in that case, here 0 and X will give 1. Okay. Now this X is here now. This 1 is here now. This 1 is here now and this 0 is here now. So this X and 1. Now what will happen here if X is and 1 passed by NAND gate? Okay. So if X and 1 is passed by AND gate, okay, the output is X because priority has been given to X. Then X passed by inverter is X. So in that case, the X and 1 is X. Okay, and 1 and 0 is 1. So again, X and 1 is X. Okay, so if uh, you have to check all the basically all 12 inputs. Okay, all 12 inputs that is 0x, x0, 0z, z0. So let's try with I tried with the 0x. Okay, let's try with the 0z. Okay, so in that case 0 and x. Okay, so let me add here value 0 and x means x, sorry, 0 and x means x and x and 0 means x. Okay, this already I have proven in other page. Okay, now okay, so now z and 0. So z and 0 means if any input is z and if any input is 0, in that case the output is 1 because priority has been given to 0. So 0 by z means 0 here. 0 by z means 0 and 0 passed by inverter is 1. That is why 1 here. Okay. So this is z, this is 1, this is 1, this is 0. So 1 and z. So what will happen if any input is 1 along with z in AND gates? 1 and z, the output is x. The output is x. So x passed by inverter is x. So here output will come x. Here 1 and 0 will give 1. So again 1 and x will be x. Okay, again 1 and x will be x. Okay, so very important topic I am teaching you here. This is a part of the digital electronics as well as this is a part of the Verilog also. Okay, if everything goes fine, then expect at least 50-60 classes. Okay, expect at least 50-60 classes in including your digital, Verilog and FPGA. Okay, up to the basic level. If everything goes fine. Okay, so this is one part. Okay, so if I X and X, okay, so again A and B. So one Z, Z1, okay, and one X and Z1. Sorry, one X and X1. This is one case. This is one case. Okay, and then XX, ZZ, ZX, and XZ. This is okay. So let's take one example of one Z and one X also. One Z and one X also. Okay. So what happened if I'm giving one Z or one X? Anything. So as we know that if I give here, this is now one Z and one X. Okay. So if I give one or Z here, okay, the priority has been given to Z. So in that case of any input Z, the output is X. X passed by inverter is X. Okay, so one Z means X. This one is here, X, X. This Z is here. So one and X inverter, sorry, one and X passed by NAND gate output is X. X and Z passed by NAND gate is output is X. So again X. So this is case of both, either Z or X. Okay. So my truth table output is X, 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 X. So this is a simple implementation of X and Z based on XOR gate. Okay. Now the XNOR is just the invert. Okay. So only changes is here. Okay. In case of XNOR, the only changes you will find here in first line, first four line. Okay. So if it is your 0, 0, 0, 1, 1, 0, 1, 1, output is 1, 0, 0, 1. This is the invert. Actually, XNOR is the invert of your XOR. Okay. So now 0x, x0, 0z, and z0. So in that case also the output is x, because this x is passed by inverter is okay. So why, okay, not this one. So if you again connect this inverter, so this is your XOR output and this is your XNOR output. Okay, so if X is coming here, then again you are getting the output X only, right? Very simple. Okay, very simple. Now A and B again out. So one Z, Z1, and one X and X1. Okay, X X, Z Z, ZX, and XZ. So in that case, output is X X X X X X X X. Okay. Now let me show you the practical aspect. Okay. I'm opening the tool here. Okay, so I will first show you the practical aspect with respect to the gates. Okay, not with respect to the HDL. Okay, okay, sorry. I have to show you with the respect to the schematic. Okay, so right click, new source, schematic, test X and Z values. Okay, on gates, on gates. So I will make a simple design. Okay, so this is your workspace. Go to symbol. Now select gates one by one. So AND 2, I will take input AND. Then OR, okay. Along with AND, I will take NAND. Okay, NAND 2. This is my NAND 2. Then I will take OR. Okay, I'm testing basically gates. Okay, NOR 2, and then XOR, XOR 2, and XNOR. This is my XOR NOR 2, and then let's take and buffer also. Take a not and buffer also, right? Simple. Not. Okay, inverter, inverter. Okay, inverter at buffer. Buffer. Okay. So now I will connect the inputs. I will take input line A and input line B. Okay, like this. So this is my input A and this is my input B. And let me connect the output also here. Output. Okay. This is my input A. A. This is my input B. Okay. Input B. Okay. Then this connect. Let's connect this input A one by one to one input of one gate. Okay. This B to input. Okay. A to NAND. This like this. Oh, sorry. Okay, like this, like this. Okay, and then A, because buffer and inverter is a single input, so I will connect both with the A. Okay, so you can connect, you can select this and you can merge with your input. And same, I have to use my mouse. Okay, oh, I'm looking for my mouse. Yeah, I think my system is, got it. Okay, so this is your input. So I will name it and underscore out, control A, control C. Okay, NAND, NAND underscore out. This is your OR underscore out. This is very strong tool. Okay, no one is using this tool. So, but I am helping my student to use to go through with this tool because this basically clear a lot of your digital doubt. So, NOR underscore out, XOR underscore out, XOR underscore out. Okay, then NOR underscore out. Oh, sorry. I think this is now XOR. Okay, this is XNOR. Sorry, XNOR, XNOR underscore out. Okay, and this is your basically inverter underscore out, and this is your buffer underscore out. So basically, I am testing all gates, buffer underscore out. Okay, so save this file from here. Go to design, select your file name, go to the simulation. Okay, minimize all open design, select your file test x7, go to the simulation. This is your design window. Design window divided into two, your hierarchy and process. Select behavior model, run. Okay, so I already proven there on paper or on board that what happen if any input is X or Z. Now you can see by default here. You can see by default. Okay, this is your by default value. Okay, if any input is Z, what happen? Output is X. Okay, if any input is Z by default, okay, between 0 to 1 microsecond, the output is X. Because A and B we have not forced. It is A and B is basically a disconnected state, floating state. Okay, we have not forced anything. So if so in that case, in both the cases, if you consider, if you go through the truth table, okay, if you go through the truth table, let's go through the truth table here. Here, in all the cases, in here, if input is XX, if input is Z, in case of AND, okay, in case of this is in case of AND, if input is ZZ, output is X. Okay, in case of NAND, if input is ZZ, output is X. Okay, and in case of sorry, this is NAND, right? In case of okay, and okay, and okay, this is OR, right? So in case of OR, if ZZ, output is X. Okay, in case of NAND, ZZ, output is X. In case of NOR, ZZ, output is X. Okay, and in case of XOR and XNOR, if the both input is ZZ, output is X. Again, if both the input is Z, output is X. So this is your default. Okay, so this is your default value in simulation. The same thing we have proven here automatically. Okay, we have proven in last 1 hour that how basically we are getting XX. Okay, let's back to screen. Simulation. See, if your input is ZZ, output is X. Okay, now let's force a simple value 0 1 1 0. Okay, so if I am giving 0 1 0 and B1 and B1, then what will happen? The simple truth table output will come here. See, so in case of 0 1 and is what 0. Okay, I will take buffer in the last. Okay, as per the sequence, and uh, and NAND, yeah, and NAND or NOR, XOR and XNOR. Okay, basically I am taking the all output in sequence. Okay, you can see here first your AND, then NAND, or then NOR, XOR, then XNOR, then inverter, then buffer. Okay, similarly, AND, NAND, or NOR, XOR, XNOR. So you can see here the inverted output you can get it in NAND, NOR, XOR, XNOR. Okay, and inverter, if I'm giving A 0, then I'm getting 1, and buffer, if I'm giving 0, then I'm getting 0. Okay, so what will happen if any input is X? What will happen if any input is X? Okay, so let's see. I have given X. Okay, so see, if any input is X, so as you know that in AND gate 0x, you will definitely get 0. Okay, and similarly the inverted of AND is NAND. But in OR, in case of OR, the priority has been given to X. Okay, so you have a 0. That is why the output you are getting X, 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 X. You can see here. Okay, except your inverter, you are getting 1 because it is connected to input A. Okay, and buffer you are getting same. So what will happen if if it is 1, if it is 1, see, here uh, I'm not a perfect in everything. Okay, I'm not able to uh, understand that why I'm getting previously also that why I'm getting Z here. Okay, I tried to solve it, but maybe in the coding they have maybe in the coding they have prescribed such values because these symbols are basically designed and saved here. Okay, so they are designed in backend in Verilog, okay, or VHDL. So while writing the Verilog and VHDL code, they may have set the output Z in case of this input. That is why I am getting the Z here. But I already proven there in case of 1 and X, practically on paper I am getting output X. Okay, practically on paper I am getting output X. Let's take example of A and B, 1 and X, and in case of what happened in case of here. Okay, X and Z. So let's solve this. Let me back to the screen. See here, in case of XOR, if I am giving 1X, okay, I am getting output X. Okay, but and in case of XOR, I am getting output X. This is correct. In case of XNOR, I am getting output X. Okay, I already proven here, right? I already proven here. Okay, so here as per the theory, the output is correct. Okay, but as per the simulation, here I am getting output Z. Okay, as per the simulation, here I am getting output Z. Okay, I don't know how I am getting output Z. Okay, maybe they have set the value inside the code. Okay, so if I take NAND is made up of and not also, so X and X will give X, and again the output is X. So I should get X, but here it is showing Z. Okay, so you can see here this is how we have tested the first gates with the help of input X and Z. Okay, so you can give any option, either you give your X and X also, or even Z also. If you give Z also, Z and X, see everything will become X X X. Even see this, your XNOR is also become X. If I give both X, the XNOR should come Z. If I give both X, see in that case also, I'm not getting Z here, I'm getting X. Okay, so this problem I faced earlier also, but still I'm not able to recall it, or I'm not able to identify that why I'm getting Z here in case of 1 and X. Okay, so team, this is all from my side. Today I have covered basically what happened if any input is X or Z in case of gate. Okay, in case of electronics, in case of digital electronics, what happened if any input will become X or Z. Okay, and I have proven it practically also. We cannot see this X and Z on FPGA. Okay, this is one thing I want to clear. This X and Z we cannot see on FPGAs. Okay, because there is no output display on LED. Okay, there is no output display on LEDs. So one more thing, X and Z is a case. X and Z is not basically a case sensitive. Okay, so we can use both small x and capital X, small z and capital Z. Okay, so in code, if you are using somewhere X, capital X, somewhere small x, somewhere capital Z, somewhere small z, then in both the cases it will not give any error. Okay, but the whole Verilog is a syntax as well as the identifiers are the case sensitive. Okay, so in any case, if you are using capital my word, okay, and somewhere you are calling small my underscore word, okay, the same program you are calling somewhere, then this will give a error. Okay, so this is all from my side. Today I have explained you the X and Z in digital. Tomorrow I will explain you how to implement this X and Z in Verilog. Okay, so we are still working on gate level modeling or gate level primitives. Okay, these are the basically a low level of abstractions. Before that, there is one more that is called a switch level modeling. Okay, so that is something different. So after the switch level modeling, this gate level modeling is the only layer. Okay, so to understand the gate level modeling, you should know the how it is working, what is the input and what is the output, right? So this is all from my side, and as I mentioned earlier, I'm trying to give the 40 to 50% of my knowledge, okay, at no cost for your better understanding. My team, Devansh and Vivek, we are trying to help you to identify your interest. That is why we are taking three things in parallel: analog, digital, programming. Okay, so this in digital also you are getting programming, and if I can say a programming which start with C, C++, Verilog, VSTL, etc. So if you are in first year, second year, third year, please identify your interest. Okay, we are working very hard to give you the basic understanding of all three domains so that you identify your interest. You should not follow the others. You should not follow the others. That means someone is saying there is a huge requirement in verification, modeling, okay, in design and verification. But if you are not familiar with, if you are not good in making the logic in C, C++ or in Verilog, please don't choose the domain. Choose something else. Don't go with any programming domain. The programming domain is your design and verification, your system C domain, your RTL design, your SOC design in FPGAs, and then in FPGA alone, FPGA is a pure coding dominated, and embedded is a coding dominated. So if you are not able to make the logic, please don't go for this domain. Think for about analog and digital like PD, PNR, synthesis, STA, DFT. And again, if you're good in analog, then go for analog. If you're good in digital, then go for this. So this is our basic objective. Okay, I know many of you are going through with your semester exam. Please focus on the semester exam. These live classes are already recorded there, and I am saving in the playlist. Go through the playlist sequence I have maintained. Today is the 18th class from 1, 2, 3, 4. Okay, so follow the each and every class. Don't go and don't jump it. Okay, go and record it. Okay, if you don't have the FPGA board nearby in your college or with you, just go through up to the programming. Okay, you should understand the complete flow which I have explained in a last class. Okay, so this is all from my side, and please keep learning. Please be focused, have a patience, and please maintain the dignity within yourself, that you should want to learn something which is already available in the market, but which is not discreted. Okay, here I'm trying to bring everything in a same in a single platform. Okay, so bye everyone. Jai Hind.